I neglected to mention that this method for demodulation is called synchronous demodulation, which means more or less with time, and it requires a replica of the carrier signal. Now I want to look at the same demodulation process, but not look at the time equations. I want to look at the Fourier transforms of these equations, and we'll start with this received signal R of t, which we have, which I've written out in this line. I'll copy that down. R of t is equal to, let me think. Let me do it this first line. X of t times AC cosine 2 pi FCT times AD cosine 2 pi FCT. We had this double sideband signal. If we looked at the spectrum for the double sideband signal, we had at this is plus FC and minus FC. We had replicas of the original message signal. This is phi, capital Phi, double sideband as a function of f. This was AC over 2 times capital X, X of f minus FC. This side is AC over 2 times capital X of f plus FC. Now, with synchronous detection, we're going to take that signal and multiply by a cosine. So that would be that would correspond to taking the spectrum of this signal and convolving with the Fourier transform of the cosine. And the Fourier transform, so we're going to convolve this with a pair of delta functions centered at plus and minus FC. They are of area AD over 2, each of them. So when you carry out this convolution, we replicate this entire shape centered at the carrier frequency on the at plus FC. We replicate this entire shape again centered at minus FC. What that's going to do is take this shape, and we're going to replicate a copy shifted back down to 0 and replicate a copy shifted up to twice the carrier frequency. Same thing with this other, for the negative frequencies, this shape will be shifted down to 0, and it will also be shifted up to twice the carrier frequency. So when, after the convolution takes place, we will have a spectrum. We'll take these two copies that are shifted back down to 0 will be added together, but it will still have the same shape as the original message spectrum, and then the two copies will be shifted out to plus and minus twice the carrier frequency, and they will be smaller copies. They'll be half size, but this now is the spectrum of the signal that comes out of this mixer, and we can demonstrate that by taking the Fourier transform of this time signal. So I'll call that capital R of f. We've got let's see, when we've got when we convolve capital X of F with a pair of delta functions. That gives us AC over 2 capital X of F minus FC. Oops, still not high enough. There. F minus FC plus AC over 2 times capital X of F plus FC. Okay, so that's the product X of T times, well, this is the double sideband signal. This is simply the spectrum for the double sideband signal. Now we're taking this and convolving it with the pair of delta functions from this replica of the carrier, which would be AD over 2 delta F minus FC plus AD over 2 delta F plus FC. And now we need to convolve these two functions over each other. And when we accomplish that, we get the spectrum of the received signal. When we convolve this pair of delta, this delta function, let's see, we would have 1/4 AC times AD. Then we take F minus FC and substitute for F in this part of the equation. So capital, instead of F, I write F minus FC minus an additional FC. That's this convolved with that one. Now this one convolved with this one, plus 1/4 ACAD, and then I take delta, and instead of F, I write in F minus FC plus FC. That was this one convolved with that one. Half finished. Now I take the second term and convolve it, so we get 1/2 times 1/2 is 1/4 AC times AD. I take F plus FC and plug it in for F here, capital X, F plus FC minus FC. And then the last term, 1/4 AC times AD. Take F plus FC and plug it in for F. In this term, X, F plus FC plus FC. And now, let me find another piece of paper. There's a piece of paper. That will do rather nicely. And write capital R of F is equal to, from this term we get 1/4 ACAD, 1/4 AC times AD times capital X of F minus 2FC, then plus 1/4 ACAD, capital, that should be a capital X, sorry, capital X, F, and then minus FC plus FC is 0, so this is just X of F. Then the third term, plus 1/4 AC times AD, capital X, FC minus FC is 0, so we just have capital X of F, plus 1/4 ACAD, capital X of F plus 2FC. So now I can combine these two terms and write capital R of F is equal to 1/4 AC times AD times capital X of F minus 2 FC plus 1/4 plus 1/4 is 1/2 ACAD times capital X of F plus 1/4 AC times AD capital X of F plus 2FC. So we sketch this spectrum and what we get is this term shifted to twice to the right to 2FC, and it has it's going to have the shape of the original message signal, capital X, shifted to the right to 2FC, and it will have a scale of 1/4 AC times AD. So this is 1/4 AC times AD. This next term is a replica of the spectrum of the original message signal centered at 0, and it has a scale of 1/2 AC times AD. The third term shifted to the left to -2FC, and it's got a scale of 1/4 AC times AD. So this is capital R of F. That is the spectrum of the signal that comes out of this mixer. Now we take this signal and we pass it through a low-pass filter. And the low-pass filter, just to make life simple, let's use an ideal low-pass filter. Here is the transfer function for the ideal low-pass filter. It would have a gain of 1. This is an ideal low-pass filter. Has a gain of 1. And the original message signal has a bandwidth of B, so it has a bandwidth sufficient to pass the original message signal. What will come out of the low-pass filter will be the product of the spectrum of the input signal times the transfer function for the low-pass filter. So what we will get out of the low-pass filter is, this is capital Y of F, and it's eliminated the two high-frequency components, and this is a replica of the spectrum of the message signal. And it only differs from the spectrum of the message signal by some scale factor. And the scale factor is not significant for us because we can always amplify or attenuate as we need in order to make the signal the amplitude we wish.